In this video, I'll be talking about what a piecewise function is. So a piecewise function is really a series of functions linked together. So what you're used to and what you've seen pretty much all of your life is f of x equals, and then there will be some sort of equation off to the side here. But a piecewise function is a collection of equations. So instead of there just being one to define it, you're actually going to have multiple. So you normally open a piecewise function with a bracket saying that everything inside of here is part of f of x. This is what makes up our function f of x. So it could be 2 equations, it could be 3 equations, it could be a list of 400 equations. All that matters is this function is defined by everything in here. So on the next couple slides we'll see some examples, but to start with, just to keep it vague, we're going to say y1. This is whatever that first function is. And then you'll have a y2, and you'll continue on for as many equations as you have. But what makes a piecewise function different is this isn't the whole y1. We'll usually have some sort of domain restriction off to the side here. So for example, we might say x is greater than 4. So what that means is our function f of x looks like y1 whenever x is greater than 4. And then the other domain restriction that we have is typically going to be something like less than or equal to 4. So what these domain restrictions say is if your x value for whatever you're graphing or whatever you're evaluating is greater than 4, you're going to look at this first equation here. But if you're looking at a number that's less than 4, you're going to look at this equation here. So that's the basic idea of what a piecewise function is. Instead of it being one equation, it's broken up into 2 or more equations. Specifically looking at these domain restrictions is going to help you evaluate them and graph them and fully understand what it is that a piecewise function is. So let's go ahead and start taking a look at some examples. So here is our first example here. As you can see, they've given us f of x, and it is made up of 2 different functions here with the domain restrictions off to the right. So I'm going to go ahead and color code because that helps me. I'm going to do this equation here in yellow, and then I'm going to do this equation here in green. So what I find helps me is to kind of get a visual of what's going to be going on here. So I'm going to actually make some dotted lines between -3 and 2. So here's our graph 1, 2, 3. So here is -3. And then between 2, 1, 2. So here is 2. So that first equation will only exist between these 2 now dotted lines. So what it says in the domain restriction is that the yellow graph is only between -3 and 2, which is why I've given these little dotted lines. I know whatever I draw has to be between these 2 lines because that function only exists between those 2 values. So now I can basically just graph this equation. If I know how to graph a linear equation, then I know how to graph this, this function on here. If you don't remember how to graph linear equations, then you might want to go ahead and review that. Currently these are both in the form of the slope-intercept form, which is y equals mx plus b. So I can look at this equation here and see that I have a slope of -1, and I've got a y-intercept of +1. So if I wanted to, I could graph those. That is dependent on you understanding how to graph linear equations. If you really don't remember how to do that, then you're not out of luck. You can also do the whole chart method where you plug in an x and you get a y. And this is actually something that I do suggest specifically for your endpoints. That way you know where your graph is going to be. So I'm going to go ahead and plug in -3 for my x value. So -3, this becomes +3 plus 1, which is 4. So the point -3, 4 is on this graph. So I can now go -3, 1, 2, 3, 4, and put a closed dot here. Now I am putting a closed dot on purpose because it says or equal to. If it says or equal to, then you know that you've got a closed dot. Closed dot means that it is included, and so I look for those equal signs. Next, I'm going to go ahead and do a 2. So plugging in 2, I get negative 2 plus 1, which gives me negative 1. So I know the point 2, negative 1 is on my graph. 2, negative 1. Again, it says or equal to, so I'm going to go ahead and put a closed dot. Now again, I recognized that this was a linear graph, so I can go ahead and actually connect these two dots because it is a linear function. Now I can go ahead and check my y equals mx plus b with my slope-intercept. I should have a slope of negative 1. I do go down 1 and to the right 1 all the way through. I do have a y-intercept of 1, so I'm pretty confident that this is a good picture and a good representation of my first equation. I have specifically made it so that it is between these two dotted lines, so this yellow equation has been graphed. Next I would move on to the green equation. So this one does look a little bit scarier because it has that fraction in there, but it's still the same idea. Your slope is 3/2, and we have a y-intercept of negative 4. And this is one place where graphing with the linear idea of looking at your slope and your y-intercept is a little bit difficult, because our restrictions for the green graph are between 2 and 6. When I go ahead and make those dotted lines, it's going to be between 2 and 6. Well, this line's already 2, and 3, 4, 5, 6. So my graph's going to be between these two dotted lines now, which you may notice is a potential issue if I want to graph my y-intercept, because this green graph doesn't exist on my y-intercept or on my y-axis. So if I were to graph this as if it wasn't a piecewise function, if I was only graphing this second equation, then I would just go down to negative 4, 1, 2, 3, 4, and then I would put my dot. I would go up 3, and I'd go to the right 2, and then I would continue all the way through there. But my graph doesn't exist on that y-axis, which is why it's a good idea to use a chart of some kind so that you know where your endpoints are. So I'm going to go ahead and plug in 2. I get 3/2 times 2 minus 4, which, let me scoot this down, give myself a little bit more space. Ends up being 3 minus 4, which is negative 1. The point 2, negative 1 is on my graph. Now if you'll notice, this is an open dot. So I would go over to here and put an open dot, but the graph already exists there. So a closed dot will always trump an open dot, and we will get that to be a closed location, because the yellow graph says that it does exist at that point. The green graph says that it doesn't exist, but the yellow graph says it does, so the yellow graph wins out. Now I'm going to go ahead and check my other endpoint, 6. So 6, 3 over 2 times 6 minus 4. Well, 3 over 2 times 6, I can simplify this down to be 3 times 3, which is 9. 9 minus 4 is 5. So the point 6, 5 is on my graph. Here's my 6, 1, 2, 3, 4, 5. It is an open circle because I'm looking at a not equal to. So let's go ahead and connect this because we recognize it is a linear equation. And here is the graph of my piecewise. Now in an ideal world, we would go ahead and erase these dotted lines, and this is what our function is going to look like. I'm going to clean it up just a little bit more. I want to make that a much clearer open dot so that whoever's looking at my paper or whoever is trying to decipher what I'm doing can clearly tell that that is an open dot. This right here is a closed dot, which is just fine. So this is our graph of this piecewise function. I went ahead and graphed it in Desmos so that we could see how our answer compares to what the actual Desmos program says, and we can see how close it is. So let's go take a look. So here is our graph on Desmos. You can see that we've got this same line here, checking our endpoints. 3, -4 exists on this graph. As we scoot on down, we get 2, -1, which does exist. If we go over to the other graph, as we slide down, we find out that it is undefined. Now, one thing to notice is Desmos doesn't tell you that something is undefined unless you hover over it. So Desmos is a computer program, and I guess they could program it so that it does show things that are undefined, but we can always just hover over it in the program. In real life, when we're graphing something that's undefined, like our endpoints here, we will always make sure to have this open dot. But I guess Desmos decided that it doesn't want to do that, and it only wants to tell you it's undefined if you hover over it. Usually in graphs that you see drawn by hand or drawn in textbooks, you'll see those open dots, so it's very obvious what exists and what doesn't, because you don't have that the ability to hover over it and see that it's undefined. But you see our graph does look the exact same as this one on Desmos, so we're on the right track. Let's go ahead and do another example then. So here is our second example. Now would be a great time, since piecewise functions really aren't too difficult, I would actually suggest you guys pausing it and trying it out on your own. And if you get stuck, I'm going to go ahead and do all these 3 graphs in order, so if you get stuck on one of them, you can kind of fast forward to where you need help. So go ahead and pause it and try it out now. Alright, hopefully you're just watching this to check your answers. It is very, very beneficial for you guys to try these out on your own before you just kind of just watch a video. Doing math is always a lot better than just watching math. So the first thing I'm going to do is look at my restrictions and give myself some color coding so that I know what's going on. And my line tool drawn, there we go. So this one I'm going to graph in yellow, and I'm going to go ahead and set those restrictions. So x is less than -4. Now this is a little bit weird because we can see that there is no left-hand restriction. It'll continue on until -infinity, which means this line continues on forever and ever and ever and ever. It does, however, stop at -4. So 1, 2, 3, 4. Right here is where my first graph just stops. So here's my little dotted line. And it'll go to -4. We do see it is or equal to, so I know I'm going to use a closed dot on this guy. So let's go ahead and write a little chart. X and Y, checking my endpoints. Well, -infinity doesn't really matter, so let's plug in that -4. Excuse me, it's not that it doesn't matter, it's just illogical to plug it in. So -4, 1/2 times -4 plus 4, that'll become -2 plus 4, giving us a +2. So the point -4, 2 is on this line. -4, 1, 2. We are a closed dot because it says or equal to. And now here, I'm going to go ahead and use that knowledge of linear functions so that I don't have to necessarily plug in another point. I can see that my slope is 1/2. So I'm going to go down 1, and then to the left 2, so rise over run. This is my second point on my line, which means I can just connect the dots. This is a linear function, so it's going to continue on forever and ever. Excuse me, let me make that a little bit thicker. So I'm going to continue on forever and ever in that direction, which means I'm going to have to put an arrow at the end of this. That way whoever's looking at my graph knows that it goes on forever. If I just leave it as, if I just leave it as this, whoever's looking at my graph will assume that the graph actually stops there. The arrow is how we're going to tell our viewers that it'll continue on forever. So the yellow graph is just fine. Let's go ahead and take a look at this green one here, from -4 to +1. So this endpoint to +1. Oop, forgot to turn on the line tool. To +1. Again, I'm going to make little dotted lines. That way, it's just a little way of me being able to see that that line doesn't actually exist. It's just a tool to help me. And because I'm using this digital board, I can actually delete these dotted lines very easily. It's a lot harder to erase a dotted line from your page. So let's go ahead and plug in our -4 and our 1. Actually, if we think about it, This is a very, very simple equation. It's silly for me to actually plug it in, but I do know that there are some people out there that just want to double check. So this is just the equation y equals 2. So if I'm making a chart, I actually find a lot of students will make a mistake with this. If I plug in -4 for x, there is only a 2 here. There's nowhere to plug in the -4. This states that no matter what your x value is, your y value will always be 2. So it's silly for me to plug that in, but I wanted to make sure to do it because there are some people that get confused by that. So when I plug in 1, well, there is no x to plug into, so again, we get a y value of 2. Both of these are not or equal to, so we're just going to leave them as open dots. -4, 2, there's already something there. And then 1, 2, there is not something there, so I'll give myself a little thicker line here. So I make an open dot, and then I connect on through. So there is blue. Let's take a look now at, sorry, that was green. Let's take a look now at blue. So graphing this very last equation, we've got a boundary that we have to draw. Oh, no, we don't. It goes on to infinity. So this is for x is greater than or equal to 1, which means I can just go ahead and start drawing that picture. So x and y. Our x coordinate is 1. So 2 times 1 plus 2 gives us 4. So the point 1, 4 is on our graph. It is a closed dot. So 1, 1, 2, 3, 4. So here's that closed dot. Now I'm going to again use my idea of slope. I will rise 2 and run 1. Rise 2, run 1. And then it's just a game of connect the dots. This will go on forever and ever in this direction. One thing that makes some students uncomfortable with piecewise functions is the fact that there's this jump here. That's actually called a discontinuity, and it's totally fine to have. So a piecewise function won't always be a beautiful, perfect line that you guys are used to. It's going to have these little kinks in it, and it's going to have what we call corners and cusps, which you talk a little bit more about in calculus. But they do have these breaks in them, and it's possible to have just full-on breaks. So for example, it is completely possible for this equation and restriction to never actually exist, in which case our graph would just have nothing between these points. And that's totally fine in a piecewise function. The piecewise function is simply following the rules that were given to you. If it says the function is there, you draw it in. If it says that nothing's there, then that's fine. So let's go ahead and take a look at this in Desmos and see how our answers compare. Alright, here is our graph in Desmos, and as you can see, we've got lines that meet up at -4, 2. If we follow this orange one, it does exist at -4, 2, and it does continue on forever and ever and ever off the side of this screen. For this green one, it is undefined at -4, 2. It's undefined at x equals -4. It is undefined at x equals 1. We've got our big old jump where the blue line exists at 1, 4 and then continues all the way up off the side of the screen. So there you have it. That's how we're going to end up doing things with piecewise functions. You may end up with holes in your graph like this. You may end up with corners and cusps. That's totally fine. The big key here is that when you're looking at your equation, pay attention to these restrictions. That's what makes these piecewise functions different from everything else that you've given, is they tell you the domain restrictions. If you were looking at just one of these graphs by themselves, so if you were looking at any one of these graphs by themselves, they would have a domain of all real numbers. But because we're part of a piecewise function, we give the domain restrictions. So we, as the problem giver, are telling you that this equation is not all real numbers. It only exists from x is less than or equal to -4. That is the only place that that graph exists. From -4 is less than x, which is less than 1. This function exists, and when x is greater than or equal to 1, this last function exists. That's the key to piecewise functions. It's basically the things that you've done before, but we're telling you where it exists.